Chapter 18, Part 1 is going to give us a little introduction into sampling distributions. So before we get into some problems here and some vocab, I want to look at this little introduction problem. So in 2005, the Harris poll asked 889 U.S. adults if they believed in ghosts, and 40% said that they did. At almost the same time, CBS News asked 808 U.S. adults the same question, but 48% said that they believed in ghosts. So for Part A, why do you think there was a difference between the two polls? And Part B, how much of a difference do you think you could expect from poll to poll? So I'll give you a few minutes here to jot down some of your ideas, and then we'll talk about answers. Okay, the first question asked, why do you think there was a difference between the two polls? One poll said only 40% of people believed in ghosts, where 48% said that they did in the other poll. So why is there this difference? I jotted down just a couple ideas here, and you might have more, you might have different ideas, and that's totally fine. One reason is that there could be a difference here is that it's just different groups of people that were asked. Maybe those groups had differences in ages. Maybe they had different locations. So maybe some people were very rural and then others were more urban. Maybe it's that location that's changing. There's tons of different characteristics that could have been different between those groups, which may have caused these difference in my percentages. Okay, maybe the method of asking the question was a little bit different. So maybe the Harris poll had people write in their response and send it in through the mail, where the CBS News, they asked them to respond online. Maybe that method of asking the question, or maybe it was the phrasing of the question that caused the differences. Maybe there was some kind of change in culture between these two. It does say that the polls happened around the same time, but maybe there was a new scary movie that came out, right after the Harris poll, right before the CBS News asked, and maybe it was kind of that change in culture that swayed more people to say they believed in ghosts. There's lots of different reasons here that we could see different results. Okay, it shouldn't be too surprising that those results were different. I'm not expecting it to be 40% exactly each time because of all of these different reasons. So how much of a difference do you think you could expect from poll to poll? Are you okay with this 8% difference? Do you want it to be lower? Do you want it to be 2%? This is really opinion-based, so it kind of depends up to you personally what you think is okay from poll to poll. This is really what we're going to look at here in our next unit, is mathematically finding out how much of a difference do we expect from group to group. Now, the first thing that we're going to look at is called a sampling distribution. Before we get into an actual example of sampling distributions, I want to show you just kind of in general what these sampling distributions look like. So I'm going to give you a visual here. Now, whenever I'm looking at data, we typically start with thinking about the population. So the population would be our large group. This is everyone that we care about. Now, from that population, we could compute some number values, right? We could find some averages or some proportions, and those are the two things that we're really going to be focusing on this unit, are proportions and averages. So if I find an average and it's coming from that population, we're going to use the Greek letter mu. So this mu would stand for the population mean. So the true average coming from that population. So that might mean average height or average weight, average GPA, but anything with averages from that population, we will use this little mu. Another thing that we'll focus on are proportions or percentages. If we find the proportion from the population, we're going to use a lowercase p. This lowercase p stands for the population proportion. And proportion would be a percentage. So it would be, 40% of people that believe in ghosts. Now, oftentimes it's very, very difficult to survey everyone in this population. So instead, what we do is we take just a small group from that population and survey them. So instead of surveying everyone here, I would take just a small group. So this is going to be a little bit of a smaller circle. And that smaller group that I'm asking is called the sample. In outcome 3, we looked at a variety of ways to get a sample, right? We looked at using a simple random sample. We looked at stratified and cluster. But now that we have this sample, we can again compute two things. We could find the means or find the proportions. If I find the mean from the sample, we would use X bar. That X bar represents our sample mean. So again, that could be average weight, average height, whatever the average is, but it's not coming from the large group, it's coming just from that smaller section. If we find a proportion or a percentage from the sample, we will now use p hat. So it's lowercase p with a little hat on top. This stands for our sample proportion. Now it's much easier to calculate a sample mean or a sample proportion because this group in our sample is so much smaller. And as long as that sample there represents the large group, as long as we've randomly selected this sample, so I'm going to say randomly selected sample, as long as this sample has been randomly selected, the sample mean should do a good job of showing us what the population mean looks like. The sample proportion should be pretty good representation of that population proportion. Now what's tricky with these samples is that I might have used a simple random sample and picked this purple sample here. You might have used a different method, so you're going to end up with a different sample. So instead I might have a different sample here, and from that sample you would still be able to calculate the mean and the proportion. Okay, someone else might calculate a different sample. You might pick a different group of people. Again, from that sample you could calculate the average and the proportion. Okay, and technically there is just an infinite number of samples that we could be choosing here, but each of these samples is likely to have a different mean and a different proportion. Okay, so if I'm using that ghost example that we saw in the introduction, the actual real proportion of people that might believe in ghosts might be 42. Okay, maybe it's 42% of people in the United States actually believe in ghosts. Now that's really, really hard for me to calculate. In order to do so, I'd have to go around and ask every single person in the United States. That's not very feasible. So instead, different groups, like we saw with the poll and CBS News, they're going to randomly pick their samples. So if this population proportion was actually 42, I might get a sample that has 40%, 48%, 45%, maybe 39%. All of these sample proportions are differing, and that's okay as we're looking from sample to sample. Okay, any number values that are coming from that population, so that mu and p, so I'm going to say population, so that's your mu and your p. This is what we call parameters. These are the true values. Parameters are very, very hard to find. It's very hard to find the true proportion of people in the United States that believe in ghosts. So instead what we do is we look for samples. Okay, from that sample is when you would have your X bar or your p hat. These values are what we call statistics. What we do is we use statistics to help us make estimations about parameters. Sampling distribution models, which is what we just saw above where we had all these different samples. So for sampling distribution models for how a sample proportion or mean vary from sample to sample allow us to quantify the variation and to talk about how likely it is that we'd observe a sampled proportion in any particular interval. So what's really nice about this is at the beginning we're like, how much of a difference do you expect? How much are you expecting of a difference from these samples here? These sample distribution models and the statistics that we'll be learning in this lesson will give us an actual number value. They help quantify the differences or the variation from samples to samples, which then we can turn these into probabilities and figure out just how likely it is that we would observe a specific statistic. Okay, sampling variability, which we'll see all the time. Sampling variability is just the differences in statistics that you observe from sample to sample. So in the beginning here, we said, how much of a difference do you expect? Are you surprised that somebody got 40% and someone else had 48%? Well, no, I'm not surprised about those differences because of this sampling variability. We understand that because we're using different random selections, my samples are going to be slightly different. What we will do is look at how big of a difference should I actually expect. Let's go ahead and do a really simplified example on the next page. All right, so here is our just very basic example. We have a bag that contains many different cards. Each card has a number on it. It's either a 1, 2, or a 3. We are going to choose 2 cards from the bag, and then we'll replace the card. So we're going to pick a card, look at it, place it back in there. So each of these is going to be an independent event because we are replacing them. We're finding what the sample distribution for the mean would look like in this scenario. So I'm going to start with thinking about this visually like we saw in the last example. So I'm going to think about my population here first. Okay, now in my population I have all these different cards, but the real thing I need to look at is the type of cards. I have a card that will have a 1 on it, there's cards with 2, or there's cards with the number 3. Okay, we are going to be choosing 2 cards, and we're going to be finding the average or the mean of those 2 cards. Now, instead of doing all these little circles kind of stemming out, I'm just going to make a table here. And in that table, I'm going to write down all of the samples, and then we'll find the average, and I'm going to use X bar there since that average that I find will come from the specific sample. So one possibility here is that I pick 2 cards that both have 1s. So I would have 1 and 1. Another option is I could get a 1 and a 2. Maybe then I get a 1 and a 3. Okay, I also could pick a 2 first and then a 1, which would technically be a different sample. I could pick a 2 and a 2, or a 2 and a 3. A few more here. I could pick a 3 first and then a 1. Could pick a 3 and then a 2, or a 3 and a 3. Okay, for each of these we're going to find the average. So to find the average we would add them and divide by 2 since my sample here was of size 2. So 1 plus 1 gives me 2, 2 divided by 2 gives me an average of 1. 1 plus 2 is 3. 3 divided by 2 is 1.5. 1 plus 3 is 4. 4 divided by 2 gives me an average of 2. 2 and 1 is again 3, so 1.5. 2 plus 2 is 4. 4 divided by 2 is 2. 2 plus 3 is 5. 5 divided by 2 is 2.5. 3 plus 1 is 4. 4 divided by 2 is 2. 3 plus 2 is 5 again, which divided by 2 gives me 2.5. 3 plus 3 is 6. Divided by 2 gives me 3. Now here are all of my different samples and the sample mean along with them. Okay, the next thing we want to do is actually make a graph or a model for the sampling distribution. So I'm going to have two axes here. Okay, horizontally, I'm going to look at the possible sample means, so the possible x values. And then vertically, we will look at the frequency in which those two occurred. So one possible mean that I had was 1, so I could start there. And out of my samples here, that only happened one time. So I would just put 1 there. My next possible average was 1.5. This happened 2 times, so now my frequency would be up here at 2. My next average was at 2, and this happened 1, 2, 3 times. I have 2.5. That happened 1, 2 times. And then I had 3, which only happened once. Okay, I'm going to give this a title here. This is technically the sample distribution for x bar, which is the sample mean. And I'm also going to say here that this is for a sample of size 2. We're only picking 2 cards, so technically this distribution is only for samples that included 2 cards. Things might look a little bit different if we were, for example, picking 3 cards or 4 cards. Now, hopefully you noticed this sampling distribution is looking a little bit like a normal model, okay? And that is not a coincidence. A lot of these sampling distributions do follow a normal model, which is very, very nice because that normal model allows us to use everything that we know about normal models. We can use our z-scores, we can use our normal CDF and our inverse norm to calculate these certain probabilities. This idea of using a normal model is actually called the central limit theorem. The central limit theorem says that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if the sample size is large enough. Okay, now in this case, our sample size of just 2 cards was large enough to create that normal model, but you'll see as we go through these examples, we're often going to be asking ourselves if we think that that sample size is large enough to create this normal model. Okay, this idea, it's amazing, it's incredibly useful because it allows us to use many variations of the normal model to analyze these different sampling distributions.